Wednesday, I'll give you a review. And then Friday, we'll give you the exam. And then my goal will be to get it graded. And then our last day, give you time to just make corrections to it. And we can wrap up grades and everything. So we'll see. All right, we're going to talk statistical inference today. Inference, all that means is to draw conclusions about a larger population based off of a sample. So you have this little diagram I put on the front here. This is kind of the way statistics works. Statistics exists because oftentimes we have dynamic populations of interest, meaning like if we think about the actual maybe United States population of citizens, that's dynamic in that it's constantly changing. There are people dying, there are people being born every day, new citizens, immigrating, et cetera, people emigrating the other way. So while once every 10 years we do try and do a census, which means to tally up everybody that's living in here, it's not a real census. You're not really getting a hold of everybody. So in that case, we developed these mathematical techniques where we can go into a population, take a sample, a subset of that population. From that sample, we'll make our statistical calculations. And then we'll use that sample to draw conclusions about the larger population, right? That's the way basic experimental design works. Today we're going to go into some further detail about some statistical inference vocab terms. So you've probably heard the term statistically significant before. And so that has a meaning, and that just means it's unlikely to occur by chance. The result is unlikely to have occurred by chance. And if it didn't occur by chance, then it usually occurred due to some cause that you're trying to study for, okay? The common levels of significant are what we call the 5% level, and that just means the probability of an observation occurring by random chance is 1 in 20 or less, or at the 1% level, which means the probability of an observation occurring by chance is 1 in 100 or less. And so just to kind of get you to wrap your mind around the idea of statistical significance, we're going to look at two examples, and I want you to try and decide if you think that the result is statistically significant, meaning unlikely to have occurred by chance, or not statistically significant, which would mean that, yeah, it could have just happened by random chance. So first one, I guess you kind of have to know a little bit about baseball, but not much. The Major League Baseball team with the worst win-loss record defeats the team with the best record. Do you think that that's statistically significant or not? Do you know how many games are in a baseball season? There's a bunch, 162. And so the idea there is even the worst teams, they win sometimes. And even the best teams lose sometimes. So even if you have the worst team playing the best team, it's pretty rare that the best team will just win every single game against them because they play each other like 40 times throughout the season. Does that make sense? So this is probably not statistically significant. It can just happen in baseball. They play so many games that sometimes the bad teams win and sometimes the good teams lose. All right, what about B? In terms of the global average temperature, the 12 years from 2001 to 2012 were 12 of the 14 hottest years on record since 1880. Is that statistically significant? Is it unlikely that it occurred by chance? Do you think it's random that the 12 hottest years happened from 2001 to 2012? Do we have any climate deniers in here? No, that's not. That's statistically significant, meaning it's unlikely that that just randomly happened in 12 years. It's likely due to something else. What is that something else? Probably greenhouse gases and global warming, right? Which has been the consensus of science for the last couple decades. So this is statistically significant. All right, another example. A researcher conducts a double-blind experiment that tests whether a new herbal formula is effective in preventing colds. During a 3-month period, the 100 randomly selected people in a treatment group take the herbal formula, while 100 randomly selected people in a control group take a placebo. The results show that 30 people in the treatment group get colds compared to 32 people in the control group. Can we conclude that the herbal formula is effective in preventing colds? All right. So in this case, yeah, it seems like less people in the treatment group got colds, only 30, whereas 32 people in the control group got colds. But that's only 2 less than the placebo, right? So do you think that that's due to random chance, or do you think it's actually the herbal supplement that is causing fewer people to have colds? That's not really a significant difference, right? In the case of the treatment group, 30% of people got colds, and 32% of the control group got colds. That's a very, very small difference, and we could probably say, yeah, that's random chance, not actually an effective treatment. Does that make sense? So we would say that result is not statistically significant, and we probably shouldn't conclude that the treatment made any difference at all. Or what we really should say is any difference better than the placebo. Because for things like colds and sicknesses like that, placebo is generally an effective treatment. If you think you're getting better, you tend to get better. And also, the negative version of the placebo tends to be true. There's studies that show, right, like couples that are married for a super long time and then one of them passes away, the other one tends to pass away at a significant rate, even if there was nothing wrong with them before. So placebo effect can actually work in both directions there. All right. Let's talk about confidence intervals. A confidence interval is just let me use a more contrasting color. It's a plausible interval of values of the parameter. So the parameter being the number that you're trying to figure out a population. So something that comes up a lot every 2 years is polling, right? When you poll about a candidate, you're trying to figure out what percent of the population is actually going to vote for this candidate. And so the way you do that is you go out, you get a sample, hopefully it's a representative sample, and you survey them. And you go, how many of you are going to vote for candidate A? And let's say that 45% of your sample says they're going to vote for candidate A. Does that mean exactly 45% of the population is going to vote for candidate A? Not necessarily, right? There will be some variability from sample to sample. If you went out there and took a different sample, you'd probably get a slightly different number. The margin of error is what is supposed to account for that variability from sample to sample. And so for a 95% confidence interval, and that just means, I'm not going to go too deep into what confidence is, but it is kind of intuitive. It means you're 95% sure that the true number falls on this interval, okay? For a 95% confidence interval, the margin of error is roughly 1 divided by the square root of your sample size. All right. So you go out, you get a sample, You measure the sample proportion. This is like the percent of people who are going to vote for candidate A. And then to that proportion, you're going to add and subtract 1 over the square root of your sample size. That gives you an interval within which you can be 95% sure the true parameter falls. All right, so let's see. Let's say the Bureau of Labor Statistics finds 3,420 unemployed people in a sample of 60,000 people. Estimate the true unemployment rate and give a 95% confidence interval. All right. So when we calculate a proportion from a sample, we give it that little hat. That's called p hat. No, I'm not just making that up to be cute. That is the statistical name of that. That's p hat. And so I went out and I got a sample of 60,000 people. And out of those 60,000, 3,420 were unemployed. And so that gives me a sample proportion of 3420 divided by 60, 123, 0.057. So that's like a 5.7% unemployment rate, right? Now, that's from a sample. So again, if I went and sampled 60,000 different people, am I going to get exactly the same 0.057? Not necessarily, right? This is basically my estimate of the unemployment rate. Now, there's going to be variability from sample to sample, which is what I want a margin of error for. So my margin of error in this case is 1 over the square root of my sample size. So 1 over root 60,000. 1 divided by the square root of 60,000. And that's 0.004. Okay, so my confidence interval, my 95% confidence interval would be so if I subtract 0.004 from 0.057, I get 0.053. And if I add 0.004 to 0.057, I get 0.060. And the way we interpret that, I would say I'm 95% confident that the true unemployment rate falls between, and I'll write these as percents, falls between, so that would be 5.3% and 6.0%. 95% confident that the true unemployment rate falls between 5.3 and 6.0%. So that's how we make a confidence interval. We start with our sample proportion, and then we add and subtract a margin of error, and that gives us an interval of plausible values of the true population proportion that we're looking for. Any questions on that? All right. So that's one type of statistical inference, is finding an interval of plausible values. Another type of statistical inference is when you're trying to make a decision between two competing claims, and that's called hypothesis testing. And so the null hypothesis, often abbreviated H with a subscript of 0, that's the claim that you assume to be true. And then we have the alternative hypothesis, which we'll abbreviate as H subscript A. This is what you're looking for evidence of. All right, so whenever we talk about hypothesis testing, kind of an analog of that in society is criminal court, right? If you are brought up on charges in criminal court, what's the null hypothesis? What's assumed about you in the United States? If you are brought into trial in criminal court, what's assumed about you? You have been charged with something, but you're presumed what? Innocent, and it is on the state to provide evidence of guilt, right? That's just like here. The null hypothesis is the thing you assume to be true. Under that assumption, you go in and look for evidence of the alternative hypothesis. The other thing is the way we conclude hypothesis tests are always in terms of the null hypothesis. You either reject the null hypothesis or you fail to reject the null hypothesis. Just like in court, what are the two outcomes? Guilty or not guilty. There is no outcome of innocent, right? It's either we had enough evidence to find them guilty or we failed to have enough evidence to find them guilty. Does that make sense? So here we're either going to reject the null hypothesis because we have enough evidence for the alternative, or we're going to fail to reject the null hypothesis. So rejecting the null hypothesis means we have evidence that supports the alternative, and then not rejecting or failing to reject the null hypothesis means we lack sufficient evidence to support the alternative. All right, so let's look at an example that illustrates the basic ideas behind hypothesis testing. This says a company once claimed that its product called Gender Choice could increase a woman's chances of giving birth to a baby girl. The company claimed that the chance of a baby girl could be increased up to 80%, but we're simply going to focus on the claim that it increases the chance of having a baby girl, meaning it gives you a majority chance of having a baby girl. What's a majority chance? More than 50%, right? Good. So one way we could test whether this claim is true is study a random sample of 100 babies born to women who use the Gender Choice product. If the product does not work, we would expect about half of them to be girls and half of them to be boys. And then if it does work, we would expect the majority to be girls, right? So we're dealing with two claims or hypotheses about this product. And here are your hypotheses. We're going to state our variable P equals the proportion born female. All right. So my null hypothesis would just be that it doesn't work. In which case, what should P equal? If it doesn't work, about how many are going to be girls, how many are going to be boys? 50-50, right? So P is 0.5 in that case. And then my alternative that I'm looking for evidence of is that it does work, in which case P is what? Greater than 0.5. That's exactly right. So those would be our two hypotheses, and that's how you can state them symbolically. Null hypothesis, it doesn't work, P is 0.5. Alternative hypothesis, P is greater than 0.5. I thought I had more on this gender choice. All right, and the way you make your decision based on this, let's say we go out, we look at these 100 babies, and we get a sample that is 55% girls out of the 100 babies. So 55 were girls. Do you think that's evidence to support the alternative? It is some evidence. It is slightly larger than 50%. But do you think 55 being born girls is convincing evidence, or could that happen just randomly? That probably could just happen randomly. What if our sample was 80% girls, so 80 girls, 20 boys? Then do you think that's convincing evidence for the alternative? Probably, right? So good, you guys have a good intuition for this. The smaller the effect size, meaning the smaller your sample differs from your null hypothesis, the less statistically significant the result is. The wider that effect size, the more statistically significant your result is, right? And so how statistically significant does it need to be? That depends on what your significance level is set to. If it's unlikely to happen randomly, like it'll only happen randomly 1% of the time, we call that strong evidence. And I would say, yeah, probably if you looked at samples of 100 babies being born over and over again, it's pretty unlikely that you're going to get that 80-20 split naturally, right? Less than 1 in 20, that's the 5% level. That's moderate evidence to reject the null hypothesis. And then greater than 1 in 20, the test is not significant. We don't have evidence to reject the null hypothesis. So I would agree with you. If we took a sample and we got 55, that's probably not great evidence to reject the null hypothesis. I mean, it's probably pretty rare that you would get exactly a 50-50 split, to be honest with you. It's more likely to be like 48-52 or 57-43 or something like that. All right. Last one. A county health official believes that the mean birth weight of male babies at the local hospital is greater than the national average of 3.39 kilograms. A random sample of 145 male babies born at the hospital has a mean birth weight of 3.61. So this is their sample. Assuming that the mean birth weight of all male babies born at the hospital is the national average of 3.39 kilograms, a calculation shows that the probability of selecting a sample with a mean birth weight of at least 3.61 is 0.032. Formulate the null and alternative hypothesis, then discuss whether the sample provides convincing evidence for rejecting or not rejecting. Okay, the null hypothesis. So here we go. Our null hypothesis, we're now talking about a mean birth weight. I'm going to call that mu. Mu is the mean birth weight in kilograms. Our null hypothesis is that the mean at the hospital is the same as the national average, which was, oh, I don't remember, 3.39. Oh, I need this. All right, so sorry, mu is the mean birth weight kilograms. The null hypothesis is that the mean birth weight is the same as the national, 3.39. The alternative, this nurse thinks they're heavier, so it's going to be mu is greater than that. So she looked at a sample of 145 babies, and in her sample, their mean birth weight was 3.61 kilograms. Okay. Well, that's definitely greater than the national average, but is that enough evidence to go, hey, this is really unlikely to have occurred by chance, and I think this hospital does have a larger mean birth weight? Well, they gave us a p-value of 0.032. That probability is the probability of getting a birth weight this large or larger if the mean birth weight is 3.39. So that's relatively unlikely. There's only a 3% chance of that happening randomly, right? So just based off of this, we said that if it's 0.01 or less, that's strong evidence. If it's 0.05 or less, that's moderate evidence. So we're saying, hey, that's pretty unlikely to have occurred by chance. We have moderate evidence favoring HA. So I'll say, our sample suggests the mean birth weight may be higher at this hospital. All right.